Hey guys, we're looking at your periodic table on page 5 and we're color coding based on the different groups that we have. So our group 1 is the alkali metals, and the alkali metals are the most reactive metals on the periodic table. They rarely are found alone in nature, and one of their cool properties is that they catch on fire and they explode when they're mixed with water. So on your periodic table, we're going to color that group in pink. So as you color this, that is lithium down through francium. And we're excluding hydrogen because hydrogen, even though it is in group 1, it is not one of the alkali metals. It's all by its lonesome. One other thing that you see here is the group number. I've circled it right here for you. So on your periodic table, you can see the group number, should you forget, just by looking in this little kind of grayed out box. So take a minute and go ahead and color that one in. Second group, these are the alkaline earth metals. They're the second most reactive metals. So one thing that you'll notice in looking at the pattern of the elements on the periodic table is that the metals are on the left-hand side of the periodic table, but the most reactive metals are to the very left of the periodic table, with the most reactive being group 1, second most reactive being group 2. The alkaline metals are used in fireworks, so next time you watch some fireworks, you can thank the periodic table. And the alkaline earth metals, the different metals produce different colors. For example, strontium is kind of a reddish purple color, barium's kind of a yellow-green, magnesium burns white. So each of them in different combinations or used individually can produce different colors. So go ahead and take a minute and color purple for your key around the box, and then color in beryllium down through radium purple. Our next group on the periodic table are the transition metals. So the transition metals I've colored in green. So they extend from group 3 through group 12. So the transition metals are this large rectangular area in the center. That's scandium down through actinium, and then zinc down through niobium. So on your periodic table and your time tracker, it may be updated and have 112 as Copernicum. So that is the UUB is the temporary placeholder name. So the transition metals in groups 3 through 12, they can be found alone in nature, and they also can be found in compounds with other elements. They are going to have a high melting point, which is really good for us because since they have a high melting point, we can use them for things that are going to get heated up. Like if you are going to bake a tray of chocolate chip cookies, then you can use one of the transition metals. Transition metals are used commonly in alloys to form pots and pans, so things that we are going to use for everyday purposes. So if it had a low melting point, for example, when you put your chocolate chip cookies into the oven, you would end up having melted metal all over your chocolate chip cookies, and that would not be good. So they have a high melting point, which means it has to get super hot in order for it to melt. And they have a low specific heat, and that just means it heats up quickly, so it is easily going to be able to change temperature. Group 13, 14, 15, and 16 I have identified here by the group name. So this family name is based on the element that is at the top of each of these groups. So boron is at the top of group 13, so it's called the boron family. Carbon has carbon family, has carbon at the top, so group 14 is carbon family. Group 15 has nitrogen at the top, so it's nitrogen family. And group 16 has oxygen at the top, so it's the oxygen family. Each of these groups is one of the mixed element groups, so we have some non-metals at the top. We've got our metalloids in the center on the staircase, and then we've got some metals at the bottom. So they have sort of a mixture, and we're going to be talking about their characteristics separately. So then we have group 17. Group 17 elements are the halogens. Your stem halo means salt, and gen means producing or origin. So literally, if you use your stems, they are salt-producing elements. They're the most reactive non-metals. They form salts during chemical reactions, and it doesn't necessarily have to be edible salt. It could be a salt residue of some kind. So we're going to color in the group 17 elements red, and color in your key around the halogens box red as well. And then our last group on the right-hand side, these elements are the noble gases. So group 18 elements are noble gases. They are, oddly enough, gases. So group 18 is our right-handmost column or group of elements. These noble gases are unreactive. They do not like to form compounds with other elements. They like to be left alone. They're also referred to as inert, I-N-E-R-T. So inert just means unreactive. They have a full valence shell of electrons. So remember, the valence shell is the outermost shell, and they don't like to form compounds. So following the octet rule, the rule of 8, our compounds, our different elements like to have 8. They like to have that full outer shell of electrons. So for the noble gases, that works out well for them because their valence shell is full. So since it's complete, they don't like to mess with other elements. They're kind of the stuck-up elements. They like to be left alone. They don't want to mess with anybody. They just want to be left alone. So that's why they're unreactive, because their valence shell of electrons is full. Down here at the bottom, we have our lanthanides and actinides. So the lanthanides and actinides are separated from the rest of the periodic table. They are metals. However, they have unique characteristics unto themselves, and that's why they are separated. And you may have noticed that there's kind of a jump in the atomic numbers here. So we go from 57 lanthanum to 72 hafnium, and that's because the rest of those elements are right here, 58 cerium, all the way over to lutetium 71. So these elements, as well as the actinides at the bottom, actually get inserted into this little spot right here where it has that jump in the atomic numbers. So the lanthanides are the top row. It's named, if you see lanthanum right here, lanthanide, so its name is corresponding to lanthanum. They are silvery metals. They have a pretty soft texture compared to other metals, and when they're exposed to oxygen, they will rust, and that term is called oxidizing. Remember, your stem oxy means presence of oxygen. And then this bottom row, these are the actinides. Again, the namesake right here, actinium, actinide. And these metals are all radioactive. So they are pretty unstable, and they will release some kind of energy in the form of radioactivity. They're weakly magnetic. And some of these elements are going to be in crystalline form, so they have specific structure with repeating pattern of the atoms. These actinides, most of them are synthetic, and that means man-made. Literally, if you use your stems, syn means together and the means put, so it's literally put together, it's manufactured. And they can be created in particle accelerators in laboratories. And you notice that a lot of these have the atomic mass in parentheses, and that's because a lot of these atoms are so unstable that as they are created in particle accelerators, as they're created synthetically in laboratories, they are so unstable that they decay really quickly. So they may only be in existence for a few seconds before they start breaking down. So scientists don't have a lot of information or a lot of information about different isotopes, different forms of some of these elements. So that's why you have just this number for the atomic mass in parentheses, because it doesn't have a nice hefty data set of the atomic masses of different isotopes like some of these other elements do.